So in this example, we're going to be looking at a energy balance ultimately between section 1 and 2, where we have some unknown turbo machine that's doing some work within our control volume. And so in this problem, we're given a whole bunch of different parameters for our inlet at section 1 and our outlet at section 2, and we are asked to solve for a few things. So to start with, in part A of this problem, we're asked to find the exit velocity v2. So it's a velocity at that section 2. And this part, if we don't know where to start, it looks like we're going to be starting with a mass balance. But before we get there, we'll write down our assumptions, which is always a good thing to do first. So first of all, I'm going to assume that there is that these inlets and outlets, lacking any information, that these inlets and outlets are 1D. I'm also going to assume, again, we're given this assumption that the flow is steady, so we're going to assume steady state. Right, so that means any of the terms that we had in our mass balance, that were t dt, partial d with respect to t, those are going to be 0. And let's see, 3. Also going to assume that there is no frictional work. We do have some heat flux, some unknown heat flux in that we're solving for in part B. And we have some shaft work out, right, that we're given. But we are still going to be assuming that there's no additional frictional work in this system. And again, remember, when we say there's no frictional work, we're not saying that there's no drag on any of the turbo machinery parts. And what we're saying is that any drag that might have happened on those turbo machine parts is just being bumped into that shaft work term. In this case, 700 horsepower that we're getting out through that turbo machine that's inside our control volume. Okay, but notice that here I'm not assuming, for example, that we have incompressible flow because we have air. We have a pretty substantial difference in temperature and pressure. And so it is very likely, in this case, we'll see definitely possible, that we're going to have a difference in density through this system. So to start with, I'm going to define my control volume, and I'm just going to draw my control volume like this around my turbo machine. Right. Note that I'm cutting my control volume through this heat term, Q dot, and this shaft work term. And what I'm going to end up with for the flow are two control surfaces, CS1 and CS2. Okay, so now in part A, trying to find the exit velocity. And so as I said, we're going to start with a mass balance, and we're going to know that m dot 1 is equal to m dot 2. And now to find that, right, we're going to say that's rho 1 A1 B1 is equal to rho 2 A2 B2. We're just going to get started. We're trying to solve for exit velocity, V2. We know V1. We let's see, we know the diameter at the inlet and the diameter at the outlet, in fact, are just equal. So actually these terms are going to drop out. But what we don't know here is rho 1 and rho 2. Right? We're given pressure and temperature, but we're not given rho 1 and rho 2. But as a hint in this problem, we're given R is equal to 1716, right? So we know we're going to have to use this perfect gas law in order to find the density of the gas. And so to start with, get started on this problem, we're going to find rho 1 and rho 2. So we're going to say rho 1 is equal to P1 over T1. We start plugging in our values. And so our inlet pressure 150, and that is pound per inches squared, times 12 inches per foot squared, over, we're going to have 1716 times, here we just have the P1, T1, which is going to be 300 degrees Fahrenheit, plus 460, transfer to Rankine, and we're going to end up with, looking at the units here on that gas constant, but what we end up with is 0.0166 slugs per feet cubed. And if we do the same for row 2, again, given all of the different terms that we have for example, the pressure at section 2, the temperature at section 2, similarly, we're going to get 0.00679 slugs per foot cubed. Okay, so now we know row 1, we know row 2. We're given V1, we have to solve for V2. And so we can simply solve for this, right, by V2 is going to be equal to V1 row 1 over row 2. If we plug in our values, this will be V1 100 feet per second times 0.0166 over 0.00679. Noting the units of row are going to cancel out in this case, and we're going to get that in order for this to, for mass in to be equal to mass out, V2 has to be equal to 244 feet per second. Okay, so that was part A, and now we have to work on part B. So now we want to find the heat transferred Q in BTUs per hour. Right, so a little bit of units conversion here as well. So for part B, we're going to start with steady flow energy equation. Right, remember, we're assuming steady state where TDT is equal to 0. And so we'll start with Q dot minus shaft work minus work due to friction is equal to, this is going to be the outflows minus the inflows. So this will be H2, right? This is the enthalpy on the way out, plus 1/2 V squared, so the kinetic energy, plus that's V2 squared, plus G Z2 times M dot, minus the same thing for the input. So it's H1 plus 1/2 V1 squared, plus G Z1, also times M dot. And now we're going to apply the assumptions that we have. Another assumption here is going to be what's this up here, Z1 is equal to Z2, or that there's no elevation change. So these terms drop out. We're also assuming no frictional work, so this frictional work term drops out. And now, let's see, we know the shaft work term. We're trying to solve for this. Enthalpies we're going to have to solve for, but we have enough. For example, we're given the heat capacity of the fluids, we can solve for those, and work our way through the rest of this. So we can rewrite this, for example, it's Q dot minus WS is equal to CP times T2 plus 1/2 V2 squared. I'm just going to gather these terms together, minus Cp times T1 minus 1/2 V1 squared times m dot. And we can start gathering these things together and plugging them in. So let's see. So we have Q dot is going to be equal to WS, the shaft work. We're given that the shaft work is 700 horsepower, and we can do a unit conversion there. Let's see, so it's going to be 700 horsepower times a conversion factor of 1 horsepower is 550 feet pound force per second. So that's going to be 550 feet per HP, plus, start plugging in terms here, the heat capacity that we're given, 6,003. I'm going to assume that all the rest of our units line up here, but it's not never a bad idea to check. 6,003 times 495, temperature in Rankine, 1 plus 1/2 times 244 squared minus 6,003 times 760 minus 1/2 times 100 squared. This is all times m dot. M dot is going to be equal to rho1 A1 V1. You can actually compute this up ahead because we dropped out the areas, but we can go ahead and find this as 0.0166 times pi over 4 times the diameter. So the diameter here is given as 6 inches. We want this in feet. So this is going to be 6 over 12 squared times 100. And this is 0.325 slugs per second. So we have that little aside. So with that, we can now go ahead and plug in the rest of our values for this. What we're going to end up with is that Q dot is equal to minus 125,000 feet pound force per second. We have to convert this into British thermal units. So we can, first of all, we have to do BTUs per hour. So let's see. So first we can do 3,600 seconds per hour. Right, noting that a second's going to drop out there. And then now we have to get to BTUs. And so we will multiply by 1 BTU per 77812 feet times force. Noting again that now this term is going to drop out, and we're left with BTUs per hour. If we plug this all in, we get Q dot is equal to minus 578,000 BTUs per hour. Let's double check that our significant digits aren't too insane. The 3 seems pretty reasonable. If we look up here, given numbers generally 1 or 2 significant digits, and so that makes sense. And there we go. So we have another thing to note here is that we have a negative amount of heat being transferred. If we come back up here to our energy balance, remember that the sign convention states that positive work, for example, the shaft work term here being positive, means that we're getting work done out of the system. and positive heat is being transferred into the system. It represents heat being transferred into the system. Um, and so, so think like a boiler or something. And so in this case, our uh, heat transfer being negative indicates that this is a loss from the control volume. Right, so think about something like a heat transfer loss through the sidewalls of this really hot vessel that's sapping some energy from a control volume, right? The type of thing that you might want to fix with insulation or something on the outside. But regardless, the fact that we're getting a negative number here means that we have a loss.